Good evening. We are now going into our next session in that chapter, Ray Optics, where today we are going to deal with refraction taking place at spherical surfaces. Now, what we dealt with in the first session was refraction taking place on plane surfaces like this, not curved. Okay. Now, refraction, as you know, is the bending of light. Conditions to be satisfied is there. That means the ray should be an oblique ray. It cannot be a ray that is passing along the normal, in which case it will not undergo any bending. It will go into the next medium without undergoing refraction. No bending will take place. So we need to have an oblique ray. Not only that, this ray should pass from one medium to another medium of different refractive index. Had it been the same refractive index, then no bending. The ray of light will continue to move in its original path. Now, here we've seen a ray of light passing from, let's say, air, that is rarer medium, into the denser medium. So, instead of continuing in its original path, it will bend towards the normal. Angle between the incident ray and the normal is called the angle of incidence. Angle between the refracted ray and the normal is called the angle of refraction. Had it been the other way around, that is, if you had allowed your ray of light to pass from denser to rarer, then the ray of light would have bent away from the normal. So Snell's law only deals with, Snell's law, we don't care about the denser or rarer or anything like that. It simply says the refractive index of the second medium with respect to first, which is N2 by N1, is equal to sin I by sin R, the ratio. Okay. So please note, second medium, whether rarer or denser, Snell's law simply says refractive index of second medium with respect to first equal to sin I by sin R. Now, for our topic today, what we are going to deal with is not plane surfaces but curved ones, spherical surfaces, refraction occurring at spherical surface. For that, I have taken the first derivation or the first case where you have a ray of light which is passing from a rarer to a denser medium, and the bending or the refraction of light should occur at a convex surface. Now let's discuss how we find out, we talk about a convex surface. Now if I draw a surface like this, then you know convexes are bulging out, and concave, I know you know that it is bulging in. Okay, that you have learned in 10th standard. Now if you look at this surface, if you're going to look from here, it's bulging out. So then you could call it as a convex surface. But if you look from here, it is bulging in. For me, it is caving in. So then it will look like a concave surface. So you need to look from the rarer side. So if this is the rarer side and this is the denser side, then this surface is a concave. Because when I look from the rarer side, it is bulging in, curving in, then it becomes a concave surface. On the other hand, had this been the denser medium and this the rarer medium, then when you look from the rarer side, you see it's bulging out. If you're looking from here, it's bulging out, and because it's bulging out, then it becomes a convex surface. So simply remember, always look from the rarer side. When you look from the rarer side, if it's bulging in, concave; if it's bulging out, convex. Also, please do not confuse yourself. This is not a mirror that we are drawing. In 10th standard, you've done spherical mirrors, but then for that, we will have a one side painted. So we'll only have one side that is a reflecting surface. So this would have been a concave mirror and this would have been a convex mirror. But then one side should be the reflecting side, the other side will be the non-reflecting side painted. We are not talking about mirrors here. We are simply talking about a spherical separation between two media of different different refractive index. Okay. So now we are going to draw the diagram, because I feel once you know the diagram, the whole derivation is very easy. Okay. So we need a ray of light to pass from the rarer to the denser medium. By convention or all our derivations, we are going to keep the object on the left side. Okay. So let me first draw the principal axis. I'm keeping the object on the left side, as I told you before. We need the ray of light to pass from where? Rarer to denser. So naturally the object has to be in the rarer medium. Let's take that rarer medium having refractive index N1. Then it has to go into the denser medium. So I'm taking the denser medium on the right side with refractive index N2. And the refraction must occur at convex surface. So we need a convex surface. I said when you look from the rarer side, it should bulge out. So my convex surface I'm going to draw like this. because when I look from the rarer side, it should bulge out. Okay. Now our spherical surface is part of a sphere like this. So the center of curvature will be lying on this side. As you know, any line, if I draw from here to the spherical surface, then that has to be the radius of curvature, simply because this line joins the center to the circumference. So it has to be the radius. And the radius of curvature, I hope you know, will always be normal to the spherical surface. So whichever line I am drawing through the center of curvature will be the normal. Okay. Now this ray of light, which is called the incident ray, that is from the object to this point, is called the incident ray, makes an angle I with the normal. Angle between incident ray and the normal is the angle of incidence. If this N1 and N2 had been the same, meaning if the ray of light is passing from one media to another media which had no change in refractive index, then no bending. This ray would have gone on to be like this, gone on in its original path. But because you allow it to pass from rarer to denser, you know that this ray must now not continue in its original path but bend towards the normal. So this is your normal on this side. So instead of going on like this, it will bend towards the normal and will give you an image here. So this is our refracted ray. Now if you take another ray along the principal axis, you know that the two refracted rays will meet here. Because the two refracted rays meets here, you will have an image, a real image, because real images are formed where two refracted rays, at least two refracted rays should meet. Now, in order to take a triangle, I'm going to draw a perpendicular down, a perpendicular here, such that I call this as NM, so that this M is very close to this pole here. Okay. Now, from here to here, this is the object distance U. This will be the radius of curvature because this is the center. And from here to here, we will have the image distance. From the pole to the image is the image distance. Then, angle between the refracted ray and the normal here. This is the normal, the line through the center of curvature will be the angle of refraction. Angle between refracted ray and normal. Now here for the object, I am going to take this angle as alpha. The angle subtended at the center of curvature I take as gamma. Angle subtended at the image I take as beta for our derivation. Okay. Now I am going to first start with Snell's law. Snell's law, I told you, simply talks about refractive index of second medium with respect to first. How do you decide the first medium and the second medium? Through where is the light entering from, that will be the first medium. To which medium is the light going into, that will be the second medium. So refractive index of the second medium is N2. So we are talking about N21, which is N2 by N1, which is equal to sin I by sin R. And as you know, for small angles, sin theta can be approximated to theta. So I'm going to approximate sin I to I and sin R to R. If I now cross multiply, I get N2R is equal to N1I, which is the first equation into which I am going to substitute values for R and I from the figure. So it's that simple. Let us look at I from the figure. This is I, which is the exterior angle to this triangle, right? So this exterior angles, it will be the sum of the interior opposite. So I may write this is alpha plus gamma. Alpha plus gamma. Then I need equation for R, relation for R. R will be equal to, see, to this triangle, you will see alpha, this gamma is the exterior angle. So gamma should be equal to sum of opposite interior angles. So gamma is R plus beta, or I may write R as gamma minus beta. So this will be gamma minus beta. I need to substitute for alpha, beta and gamma because our whole aim is to finally find a relation between U, V, R, N1 and N2. We are somehow trying to relate the refractive index of the two media, the image distance, the object distance and the radius of curvature. So I've got I in N2 and N1. I need to bring that in terms of U, V and R. Okay. So what I'm going to do is tan alpha, which can be approximated to small angles. If tan theta is small, tan theta is approximated to theta. This is going to be equal to See, tan alpha from this triangle here will be opposite side by adjacent side. So that will be NM by MO. Similarly, from the figure, tan beta can be approximated to beta. This will be the triangle we are looking at. Opposite side is NM, adjacent side is MI. So this is going to be NM by MI. Similarly, from the figure, tan gamma approximated to gamma is going to be from this triangle here, NM by MC. So this is NM by MC. Now our work is all done. We are just going to substitute all this in our first equation. Okay. So when I substitute that in my first equation, I will now have N2 bracket R is gamma minus beta. So I have gamma here, which is Nm by Mc minus beta will be Nm by Mi. Close the bracket. We have this equal to N1 bracket I. I is alpha plus gamma. So that will be Nm by alpha is what? Mo plus gamma will be Nm by gamma is for us Mc. Okay. Now you will see that this Nm is common to all the terms. So I may cancel that and write. So I may cancel that and write. This next step I'm going to do is N2 bracket. I've cancelled this because it's common everywhere. 1 by MC. Now by sign convention, you've already done that in 10th standard. Sign convention. That is, direction of incident light is taken to be positive. Opposite to that will be taken as negative. Our direction of incident light, you see, is going to the right. So to the right we'll take as positive. To the left we'll take as negative. So here we have NC. That is, from M to C, I'm measuring to the right. That will be plus R. So that will be 1 by R minus 1 by Mi. So from here again I am measuring to the right, which will be plus V. So this is V, close the bracket, equal to N1 bracket. I have 1 by Mo. So from here I am measuring to the left. So that will be minus U. So 1 by minus U, and this we have 1 by NC from here to the right will be plus R. I am simply going to rearrange this, which means I am going to put this as N2 by R here, plus I am going to bring this N1 by R to the left. So this will be N1 by R, common R. Common R is equal to, here N2 by V is a negative, so I will take it to the right as N2 by V, and this will be minus N1 by U, which is what we wanted. Very important relation that connects the refractive index of the two media, N1 and N2, to the radius of curvature, the image distance and the object distance. When a ray of light passes from rarer to denser medium, refraction occurring at convex surface. I told you, when you look from the rarer side, bulging out, so it's the convex surface. So this relation is also very important for you, because we need this for our derivation on Lensmaker's formula, and also for lots of sums and application questions. Okay. Now the same thing I'm going to do for a ray of light that passes from denser to rarer medium. Same relation. We need to find a relation between N2, N1, V, U and R. If a ray of light is passing from denser medium into the rarer medium, but refraction occurring at the same thing, convex surface itself. Okay. So here we'll change the question to denser, from denser to rarer medium. It'll be easy for you because we are going to do the same procedure. So first, I told you, if you know the diagram, then the derivation is actually very easy. So we will now draw the principal axis. I will take, so I told you, we take the object on the left side always, okay. So ray of light has to pass from denser to rarer. So the object has to be in the denser medium. Let me take it as N2, because then final there will be no confusion. Denser medium, for these derivations I am taking as N2. And it is going into the next medium, that is a rarer one, so N1. Now refraction is still occurring at convex surface, right? So I need to look from the rarer side and make sure that my surface bulges out. So I told you convex is when you look from the rarer side, it's bulging out. So since this is part of a sphere like this, the center of curvature must lie on this side, not on the other side. Now any line that I may draw through the center of curvature, you know, happens to be the normal because that's the radius of curvature. Now from here I'll take the incident ray. So the angle between the incident ray and the normal that we have drawn is our angle of incidence. This ray, instead of going on in its original path, because it is passing from denser to rarer, from here it is bending. This is a normal, right? So instead of bending towards a normal, it will bend away from the normal and form the final image here. So this is the refracted ray forming the final image with another ray that comes along the principal axis. So we have two refracted rays meeting at this point to give you a real image. So this angle between the refracted ray and the normal we take as angle R. And as usual, in order to get a triangle, I'll just approximately draw a normal so that these are very close to each other, these 2 points. So this is going to be the radius of curvature. This is going to be the object distance and this is going to be the image distance. And just like before, we're going to start with Snell's law. I'll repeat, Snell's law always talks about refractive index of second medium with respect to first. Our ray of light is entering here, so this is the first medium, going into this medium, so this is the second medium. So refractive index of the second medium with respect to first will be written like this, equal to sin I by sin R, where we will approximate I, sin I to be I by sin R to be R. Cross multiply and you have N1R is equal to N2I. Into this equation, we are now going to substitute for R and I. So from the figure I have got as, see, because this is I. Oh, we already remember, like the last time, for object we take angle subtended as alpha. For center of curvature we take it as gamma. For the image we take it as beta, just like before. Okay. So I should be equal to gamma minus alpha because this is the exterior angle. So it should be equal to alpha plus I. So from here we know it is going to be equal to gamma minus alpha. I equal to gamma minus alpha. Similarly, R is going to be equal to, R is here. So this is the exterior angle to this triangle. So R, the exterior angle, should be sum of gamma plus beta. So that's what I'm going to write here, gamma plus beta. We already know tan alpha from here should be equal to what? Approximately alpha. Tan alpha will be from this triangle Nm by Mo. So Nm by Mo. Similarly, tan beta approximated to beta is Nm by Mi. This is beta. So from this triangle Nm by Mi. And tan gamma, it will be Nm by Mc. Like before itself. This triangle Nm by Mc. Just like the before, what we did before. So we're going to substitute that all that in this equation. So we have N1 bracket. R is here. Gamma will be Nm by Mc plus Nm by Mi. From here. This is equal to N2 brackets. I is here. So that will be Nm by Mc minus Nm by Mo. From here. Nm by Mo and Nm by Mc. Nm is common everywhere. So I may write this as N1 bracket 1 by Mc. This from here I am measuring to the left, so negative. So this will be minus R plus 1 by Mi. From here I am measuring to the right, which is V. This is equal to N2 bracket 1 by Mc again to the left minus R minus of Mo again measured to the left. So this is minus U. So minus of minus will become plus U. I'm going to rearrange this to right. We have this N2 by R as negative, right? So it will come to the left as N2 here we have a minus N1 by R equal to, here we have this N1 by V, and here we have this N2 by U. So I'll rewrite it as N2 by U, bring it to the right, we have N1 by V. Okay, so this is what we have now, but I would like you to rearrange this and learn it in this way. See, I can give a negative sign to this side and a negative sign to this side, so that this will now become N1 minus N2 by R is equal to N1 by V minus N2 by U. So I've rearranged it using that negative sign simply because I feel it may be easier for you to learn this, because you remember in the previous derivation we got N2 by N1 by R equal to N2 by V minus N1 by U. This was the derivation when a ray of light passes from rarer to denser. This was our equation. Now we got a ray of light passing from denser to rarer. We have just switched the we have just switched the N1 and the N2. So when you learn this derivation, the final formula, all you need to remember is wherever N2 comes you put N1, wherever N1 comes you put N2. So this becomes N1 minus N2 by R equal to N1 by V minus N2 by U. Okay, so to learn it, that will be easier, I think, and that is why I asked you to rearrange it. Okay, so that's all we need to do today. Next class we will go into lens maker's formula. Thank you.